Hello, welcome to this lecture on modeling, analysis and estimation of three-phase unbalanced power network. From today, we will start looking into the aspect of three-phase transformer modeling. So, our topic which we start from today is three-phase transformer modeling. So, when we talk about a three-phase transformer modeling, essentially we are talking about the modeling in terms of admittance matrix. So, we are talking about the admittance matrix representation of three-phase transformer. So, what we exactly are trying to do? So, let us first understand that and then we will go into the detail. So, now for example, if I have got a three-phase transformer and let us say that I have just a block three-phase transformer, three-phase transformer, and please note that this three-phase transformer can be of any type. For example, this can be of YgYgX, X is nothing but the vector group, So, it also can be, let us say, YyGx, it can be also, let us say, YgYx, it also can be say YgDx, it also can be say YDX, it also can be say DYGX, it also can be DYX, and it can be also DDX, anything we are talking about. So, here of course, this is the connection for the primary side and this is the connection for the secondary side. Similarly, this is primary. So, then basically the first one is the connection for the primary side, Y stands for the star connection, YG stands for the neutral grounded star connection, and D stands for the delta connection. So, these are the standard notations what we are going to follow. And X, we said that it is basically a vector group, and we shall talk about this vector group in a little while. Now, here, so when we are talking about here, when we are talking about the three-phase transformer here, we are actually talking about any generic type. So, we are not talking about any specific connection type. So, this block can be of any of this type of transformer, any of this. So, then therefore, essentially this is nothing but a kind of very generalized representation. Now, what happens that it has got basically two sides. So, this is the primary side and this is the secondary side. So, this is the primary side, this is the secondary side. At the primary side, I have got ABC, capital A, capital B, capital C. They stands for the ABC, and this is VA, VB and V small c. So, capital C stands for primary side and this small c stands for the secondary side. And then we do have currents, primary current IA, line current IB, then IC, capital C, and then of course at this side is also I small a, I small b, I small c. So, then therefore, when we are thinking about any generic three-phase transformer, It has got 6 voltage quantities V capital A, V capital B, V capital C, that is corresponding to the primary side, and also V small a, V small b, V small c, these 3 correspond to the secondary side. And we have also got 6 current quantities I capital A, I capital B, I capital C, I small a, I small b, and I small c. Now what happens is that we wish to represent this transformer by this kind of a relation. So, we wish to express all these 6 currents IA, IB, IC, and then I small a, I small b, I small c. So, when we are talking about the admittance model, essentially we are talking about the representation of the currents in terms of the voltage. So, here so it is V capital A. So, some matrix representation. So, you see, so I have got, so now it is a 6 cross 1 vector. So, this is also a 6 cross 1 vector. So, then therefore, this would be a 6 cross 6 matrix. Now, this quantity, now this relationship is basically in the form of I is equal to YV, where I is the vector of currents and V is the vector of voltage. So, then therefore, this matrix will indeed denote some kind of admittance matrix. So, when we are talking about admittance matrix representation of a 3-phase transformer, we are essentially talking about the determination of this admittance matrix, 6 cross 6 admittance matrix of a transformer. So, essentially, I mean, that is the case. Now, what happens is, ultimately our goal is to use these transformer models into the analysis of a large 3-phase power network. Now, as it turns out, of course, we will show that why that is the case in this course only in due course of time, but as of now we really cannot show it, but we will show it let us say, I mean, a little later on. It helps, instead of having IA, IB, IC and I small a, I small b and I small c, it helps to incorporate this admittance matrix into the overall representation of any general 3-phase network if, instead of having this I small a, I small b and I small c, if I do represent this Y bus matrix by this. So, instead of having, so instead of instead of that one which is said, what we are interested is the representation of this. So, what we are interested is the representation of VA, VB, VC and then VA, VB, VC. So, this is also a 6 cross 1 vector. So, this is also a 6 cross 1 vector. So, obviously, this also would be a matrix 6 cross 6 matrix, but then obviously some of the elements of this matrix would be negative as compared to those corresponding elements in this matrix, because now we have taken these currents to be negative. So, essentially, as a circuit component, our representation is something like this, that I have got a 3-phase transformer three phase transformer, and I have got so this is V capital A, and because we have taken minus IA, minus IB, minus IC, so now the direction of the currents is here opposite, and this is VA, VB. So, the generic admittance model we are seeking, which we are seeking, is essentially the relation of the current and voltages, in which both the currents at the primary side as well as the currents in the secondary side are entering into the transformer, right, and we are simply seeking that corresponding matrix. So, here this is very important, where IA, IB, IC and I small a, I small b, I small c both are actually entering into the transformer. In contrast, if you look at this representation, here IA, IB, IC, they are entering the transformer, but at the secondary side these currents are going out of the transformer, right. So, but here in this representation, the currents at both the primary as well as the secondary side are both entering the transformer, and we are seeking this matrix. So, here because it is a 6 cross 6 matrix, so we can partition it into 4 matrices. So, this is Y1, we call it Y2, we call it Y3, we call it Y4, and each of them would be 3 cross 3 matrix. Right. So, our task is to essentially determine these 4 3 cross 3 these 4 3 cross 3 matrices Y1, Y2, Y3, Y4. So, we will see some examples. Now, there is a certain definite process to determine these 4 matrices for any given most commonly used transformer connections. So, we will see that how to go about this with some concrete examples. Very shortly, we will start one of the example just today itself. But before that, so some kind of notation. So, we define certain vectors. So, I, A, B, C vectors I define as I, A, I, B, I, C, and I also define this vector I small abc vector as, let us say, minus IA, minus IB, minus IC. Please note here minus IA, minus IB, minus IC are, I mean, we can also take this as IA, IB, IC if we pictorially if we are clear about this representation. So, then therefore, if we are using this representation, so in that case our vector would be just IA, IB, IC. So, for this representation, or rather for this particular circuit representation of the 3 phase transformer, so this would be the vector IA, IB, IC, right. So, that must be clear. On the other hand, if our circuit representation of the transformer is this, then this vector IA, IB, IC would be essentially minus IA, minus IB and minus IC. So, we must be clear in our mind that what kind of pictorial representation we are talking about and what is the corresponding vector we are thinking. Okay. So, now with this, and then of course, we have we also defined in similar vein V A B C, V capital A, V capital B, V capital C, and V small a B C is V small a, V small b, V small c. So, if this is the representation, so then therefore this matrix can be represented as simple that I A B C and I A B C is nothing but y1, y2, y3, y3 and y4. So, that would be the vector representation. So, from this we can get this. So, obviously our relation would be I A B C would be y1 V A B C plus y2 V small a b c and I small a b c is y3 V small a b c. So, these would be the relations. So, as we said that when we are talking about a transformer model, we are simply talking about the determination of this 6 cross 6 matrix, or in other words we are simply talking about the determination of this 4 3 cross 3 matrices y1, y2, y3, y4. Now, for any given transformer connection, how to go about it? So, there are certain methods. So, let us start looking into this. So, this is the basically the general framework. So, we are talking about y1, y2, y3, y4. Now, how to go about it? So, let us start with a very simplest possible example. Let us first start with an YgYg X transformer. So, when we are talking about YgYgX means that the primary side is also Y grounded, secondary side is also Y grounded, and X is the vector group. Now, because both are of the same type, so X can have values only 0, 2, 4, 6, 8, 10. And what does it mean by this 0 to 4, 8, 6, 8, 10? They would be nothing but, so then therefore, they simply denote the angular difference, or rather basically the phase difference between the phase A voltage of the primary side and the phase A voltage in the secondary side. So, then therefore, for any given value of x, the phase difference between the phase A voltage of the primary side and the phase A voltage of the secondary side is x into 30 degree. So, as an example, if x is 2, for x is equal to 2, so then the phase difference would be 2 into 30, that is 60 degree, correct. So, obviously, and of course, I mean x, now of course, here if x is equal to 12, so then obviously 12 is nothing but 12 into 30 degree means 360 degree, 360 degree phase difference means they are again same phase. So, then therefore, x can only be a value, have the 6 values 0, 2, 4, 6, 8, 10. So, now we would like to find out that how to find out the admittance matrix for this type of transformer. Now, we will just look into 1 or 2 examples out of this 6 just to look at the process, and by following the same process we can find out the admittance matrix for any type of transform. So, to do that, what we first do is that now we have got certain assumptions. Assumption number one is that that basically every three phase transformer is actually constituted by three single phase transformers. We are essentially talking about that kind of thing. It is just for the purpose of modeling. It has got nothing to do with actual construction of the transformer. It is just for the sake of modeling and just for the sake of understanding, we are just doing it. So, three single phase transformers. So, essentially we are talking about three different windings: phase A winding, phase B winding and phase C winding. Second assumption is that we are going to neglect the magnetizing component of the model. So, every transformer winding would be modeled by only its own leakage impedance, or let us say leakage admittance. So, we are not going to consider the magnetizing reactances of a magnetizing circuit of the equivalent any single phase transformer model. So, that we are not going to discuss. And we are also going to look at that what is the dot convention. So, when we are talking about a dot convention, just for a very quick recollection, if I have got a dot, so if this is the primary side and this is the secondary side and I have got dot here. So, if this I say that it is V capital A and this is V small a and this current, outgoing current is I A and incoming current is I capital A, then we say that VA and VA, they are in phase, and I capital A and I small a, they are in phase A. And if I take that the ratio is 1:1, for example, so then therefore of course VA and V small a would have the same magnitude and I capital A and I small a also would be of the same magnitude. And if there are dots, then VA and VA would be in same phase and I capital N and I small a would be in same phase. We need to be careful here in the primary side. So, then therefore, here when you are talking about the current, so the current entering one dot terminal would be in phase with the current leaving that dot terminal. So, that is most important. So, this we need to remember. So, IA which is entering the dot at the primary side would be in phase with the current IA which is leaving the dot in the primary side. So, let us take an example. So, let us take the very simple example, simplest possible, YgYg0. So, x is equal to 0. That means, so when I am talking about x is equal to 0, so that means there is no phase difference between the primary side and the secondary side, right. So, how to go about it? So, what we do is that we take three windings. Right, and we mark the dots. Dots are very important for the sake of modeling. We mark them with some names. Terminal name A1, terminal A1, terminal A2, terminal B1, terminal B2, phase B, phase C, terminal C1, terminal capital C2. So, this side is primary side, this side is secondary side. So, this is understood. So, this side is primary side and this side is secondary side, and we also mark the terminals here: A small, A1, A2, B1, B2, small c1, small c2. So, these are the terminal marking. We have not made yet at any connection. And now, because this side is YG, so what we do is, so I make the first connection. I simply connect A2, B2 and C2 together and ground it, and I say that this is phase A, this is phase B, this is phase C. So I say that this is IA, I say that this is IB, I say that is IC. So these are the currents. Now we draw the vector diagram. Now here one thing we need to understand, because these two voltages are in phase, so then in phase, so there be VA and there be VA. So this we must understand, right. So basically these two voltages would be determined by two parallel vectors. That is obviously very trivial. Now we make the phasor diagram. So the phasor diagram is at this primary side, this is grounded. So this is phase A, this is phase B, this is phase C, and let us make some. Now here what we have done, we have basically connected, see from this diagram if you look at, we have what we have done, A2, B2, C2 we have connected together and grounded. So then therefore as far as terminals is concerned, it is A1, so sorry, this is A1, this is A2, and then again this is B1, this would be B2, and this is C1, this would be C2. So here you see, so that is, so I mean whatever connections we have made, that is also being reflected here, that A2, B2, C2 we have connected together and grounded, and from side A we have taken phase A. So this is B and this is C. So this is C. Now at the secondary side, because x is equal to 0, so then therefore there is no phase difference. So then therefore this also would be exactly the same thing. There is absolutely no phase difference. So this is also VA, this is also, or rather this is also A, I would say that is A, and this is phase B, small b, and this is phase small c. Now you see, because now what we do is that because there is no phase difference, so then therefore this and this they are parallel. So then therefore if this is A1, A2, so then therefore here for example if I say that this is A1, this is A2 and this is A1, this is A2, so then obviously as far as this terminals is concerned, and because they are in phase and because they are in parallel, so it will be also A1, A2. Right. So then therefore we also mark the same terminals from here. So A1, A2, and here also B1, B2, here also small c1, small c2, and we ground it. And from here I take A, from here I take B, and from here I take C. Now so here, so from this vector diagram now we make the connection here. So what is the connection says? That when YgYg is 0. So first we have made the connection here, and then we have drawn the vector diagram at the primary side. According to the connection made by us, we have marked the terminals at the primary side. Then looking into the phase difference between the primary side and the secondary side, we have drawn the vector diagram at the secondary side, and then we have identified the parallel vectors, and then on these parallel vectors we have marked the terminals, and those terminals give us the connection. For example, here the connection says that again also here at this also side also we should take A2, B2, C2 together and then put them together and then put them to ground. So, then therefore, it is A2, B2, C2, I put them together and put them ground, and from A1 terminal I will take phase A, and from B1 terminal it is phase B, and from C1 terminal it is phase C, right. So, and from C1 terminal it is phase C, correct. And so then therefore, and here if this is IA and this is IA, this is IB, this is IC. This is of course I capital A, I capital C, I capital C. So, for an YgYg0 transformer, this is the vector diagram and the corresponding connection diagram. So, with this we will now proceed to find out the admittance matrix, and that we will continue in the next lecture. Thank you.